So in an earlier lecture, we defined a nucleophile in the following way. We said a nucleophile is a Lewis base that displaces the leaving group on the substrate. And we said the general form of a nucleophile is simply Nu, which stands for nucleophile, and our pair of electrons. Now, in an earlier lecture, we spoke about the size of the substrate, and we said that the larger our substrate is, the slower our Sn2 reaction is, because the nucleophile finds it difficult to get to the carbon because of the large size of the substrate. Now, in this lecture, we're going to discuss the size of the nucleophile and how its structure affects its Sn2 reaction. Does size matter? Well, we'll see in just a moment. Let's examine the following two reactions. In this reaction, we have a relatively small nucleophile attacking with its lone pair of electrons this carbon, displacing this bond along with the leaving group, forming the following two products, our leaving group and our new substrate. Now, this reaction goes in the forward as well as reverse. So that means in reverse, this acts as a nucleophile attacking this carbon, displacing this leaving group. Now let's examine the second reaction. In this reaction, what we did is we replaced these relatively small H atoms with these relatively large tert-butyl groups. So now let's suppose our reaction takes place. Lone pair of electrons attacks this carbon, displacing the leaving group, forming our two products, leaving group and substrate. And let's suppose our reaction takes place in reverse as well. In reverse, this pair of electrons attacks this carbon, displacing this bond, forming our two reactants. So, let's discuss the rate of these two reactions. Which one is faster? Which one is slower? Now, if we look at our substrate, notice our substrate has the same exact structure in both cases. That means we can't look at the substrate because it won't help us determine the relative rates of our reactions, because these two substrates are the same exact substrates. Now, if we examine our nucleophiles, we will see a difference in size. This nucleophile is much less bulky, it's smaller because it has these small H atoms. Recall that H atoms and atoms in general have the protons in the nucleus and electrons orbiting the nucleus. Now, these guys will have electrons orbiting the H atoms, and these also, these atoms, these H atoms, will have electrons orbiting the nucleus. Now that means if this H atom gets too close to this H atom or any of these H atoms as our nucleophile is approaching the carbon, if those electrons get close, we will get electrostatic repulsion between our electrons, and this will decrease the rate of our reaction. It will slow down our reaction. Now luckily in this case, these H atoms are relatively small, and there will be no bumping or very little bumping, and so this pair of electrons and this nucleophile will have an easy time getting to this carbon atom, displacing this leaving group and forming our products. Now, we can't say the same thing about this reaction. Why? Well, because now, instead of the relatively small H groups, we have the relatively large, bulky tert-butyl groups. Now, these groups will have carbon atoms as well as H atoms, and each of those atoms will have electrons orbiting the nucleus. And that means as this pair of electrons tries to get to this carbon atom, what happens is these groups bump into these H atoms, and that creates electrostatic repulsion, pushing back our nucleophile. So that means this reaction will be much slower. It will have a much smaller rate. Why? Well, because of the size of this nucleophile. The larger our nucleophile is, the less likely our Sn2 reaction will take place because of electrostatic repulsion between the electrons on the groups and these H atoms here. So once again, to overview, the size of the nucleophile does in fact affect its ability to displace the leaving groups. The larger and the bulkier the nucleophile, the more difficulty it will experience trying to get to our carbon atom. So Sn2 reactions slow down when our groups on our nucleophile become larger. So So earlier we defined a nucleophile in terms of a Lewis base. But this isn't actually correct because a nucleophile and a Lewis base are two different things. So one way of defining a Lewis base is by saying that it has a lone pair of electrons. And so does a nucleophile. And that's why we use this definition. But a Lewis base is actually a molecule that competes for the 1s orbital of the H atom. And the nucleophile is a molecule that competes for the 2p orbital of the carbon atoms. So yes, both the nucleophile and the Lewis base have a lone pair of electrons, but nucleophile competes for the 2p orbital and the Lewis base competes for the 1s orbital. So they're not exactly the same thing. So we can't say that if we have a molecule that's a good Lewis base, that molecule is also a good nucleophile. That's not actually correct. But what exactly is a good nucleophile? Well, a good nucleophile is a good competitor for the empty 2p orbital of the carbon. Remember, this pair of electrons competes for the empty orbital of our carbon atom, of this carbon C bond. So that means that when this reaction takes place, and a good Sn2 reaction is a reaction in which there's a good competition, there's a good overlap between this orbital, where these two electrons are found, and the orbital of this carbon. If we have good overlap, that means we have a good nucleophilic reaction and a good Sn2 reaction. Now recall that substitution, or an Sn2 reaction, is a reaction between the HOMO, the highest occupied molecular orbital of our nucleophile, and the LUMO, the lowest unoccupied molecular orbital, the 2p orbital of our carbon atom. So, therefore, whenever we say we have a good Sn2 reaction, that means we're saying that the overlap of the HOMO and the LUMO is a good overlap. It's a stabilizing overlap. So we create a good overlap, or a good sigma bond, in which our two electrons are found. Now we also create this anti-bonding molecular orbital, but our electrons don't go into that orbital because it's higher in energy. So, once again, the more overlap between the HOMO and LUMO orbitals, the stronger and more stabilizing the bond, the better the Sn2 reaction. So once again, a good nucleophile is really a good molecule that overlaps well with our empty 2p orbital. If the overlap is poor, we say that the nucleophile is a poor nucleophile. So, let's examine the following halogens. So let's begin with this side. Notice as we go from fluorine to chlorine to bromine to iodine, our Lewis basicity increases going this way. So our fluoride is a much better Lewis base than our iodine. However, if we look at the nucleophilicity, we see that as we go in the opposite direction, our nucleophilicity increases. So, iodine is a poor Lewis base, but it's a very good nucleophile. While fluoride is a poor nucleophile, but a very good Lewis base. So, this fluoride atom competes very well for the 1s orbital of the H atom, but it does not compete very well for the 2p orbital of the carbon. Why is that? Why is there this discrepancy? Isn't a Lewis acid, or isn't the Lewis base, a molecule that contains a pair of electrons, and isn't a nucleophile a molecule that contains also a pair of electrons? So shouldn't they attack the same exact orbital? Well, the answer lies in the following explanation. So whenever our reaction takes place, it takes place in a solvent. And solvents usually stabilize our products. So let's suppose we have the following container. Inside this container we have our nucleophile and our substrate that contains our leaving group. And the solvent found inside this container is a protic polar solvent. So let's say it's water. Product simply means this solvent can donate an H atom. And polar means the bonds are polar. So the OH bonds are in fact polar. So, what happens in solution? So if we place our fluoride into our solution, so our nucleophile is the fluoride, that fluoride is a very good Lewis base. That means it will compete very well for the 1s orbital of the H atom. And because we have a product polar solvent, we have a solvent that contains an H atom, this fluoride will take away that H atom more likely than it will attack this R group, attack this R, displacing the L. So when we place fluoride into solution, the fluoride will not be a good nucleophile because it's going to be a good Lewis base. On the other hand, if we place iodide, iodide is a poor Lewis base, and that means if we place our iodide into solution that has a product polar solvent, it will not want to take that 1s orbital, it's going to want to take that 2p orbital. And that's why we have the difference. So, in solution, the nucleophile has to make a decision. Will it act as a Lewis base or as a nucleophile? Fluoride is a much better Lewis base than the nucleophile, and so it will take the H from the water. Remember, a Lewis base takes the H atom, H ion. On the other hand, iodide is a poor base, and so it will take the 2p orbital of the carbon and will act as a nucleophile. Now, if we remove the solvent, if our reaction takes place in the gas state without the solvent, nucleophilicity will increase this way. If we remove the solvent, our fluoride atom will be the best nucleophile, and our fluoride will also be the best Lewis base. Once our solvent disappears, we no longer have the stabilizing effect of our solvent, and that means our fluoride will be the best Lewis base, and also it will be the best nucleophile. But if we have a polar product solvent, our iodide will be the better nucleophile because our fluoride is a better Lewis base than it is a nucleophile.